All right. Where do we go? The topic is lenses. Lenses. Still on the refraction of light. I said there are two types of lenses we use. Two types. You have I'm going to use a yellow marker, convex lens. It's also called converging lens. Converging lens. Diverging lens, yes. Concave is like this. It bulges out like this. Okay, then the other one is concave. Concave lens or diverging lens. It's as a result of what it does to light. For a concave lens, a light that passes through a convex, let's start with convex. In fact, we'll eventually deal with convex, but I'll just give you an overview of both. For a convex lens, if a light passes through a convex lens, it focuses. That's what I drew here in the next page. So I will just zoom it in for us to see better. So this is a convex, right? Ray of light incident on a concave lens, or a beam of light incident on a concave lens. We come out, convex I meant, let me not be mixing this thing up again. A ray or rays of light incident on a convex lens, we come out and focus, converge. That's why it is called a converging lens. The other one, when the ray of light passes through a concave lens, they will diverge. So I will mention it in passing because, as I've said, it is not in your syllabus. So I will just mention these two in passing by way of drawing diagram to illustrate what happens. If you have a concave lens, convex lens like this, and you have rays of light coming in, whether it is you have parallel rays or any rays at all, when they come out, they will. Now I'm talking about convex. Convex will converge. You meet at a point we call the focus. It can be principal focus depending on something I'm going to explain to you. That's a focal point. But I'm going to explain something to you. Anytime you're drawing ray diagrams, it's always necessary to add arrows. So I'm going to add arrows to show. Okay, so I already have one.
They even pass that point.
Yeah, they pass. It's just that they converge, and then of course, if there's no screen here, they converge and scatter again. That's why, as you're going to see, because we're going to carry out some experiment here, when the rays of light converge at a point, where they converge is where you are going to have the sharpest light. If you move towards it, it gets blurred. Away from it, if you move towards the lens from the converging point, the focal point, like I said, it is at the focal point that you have the sharpest light or image. If you move further away from the focal point, maybe towards the lens, it gets blurred. From the focal point away from the lens, it also gets blurred because it's at the focus that they all meet, so you have the sharpest image or light, as the case may be. So that's for converging lens, convex or converging lens. Okay, so for concave, I'll just explain it to you and then we move forward. So I will just a sketch will be enough. For concave, a ray of light that enters in, like I have these rays, will also change direction as they strike this plane we call the vertical plane of the lens. This plane is the vertical plane. This plane is the vertical plane of the lens, the vertical plane. Once they strike the vertical plane, they diverge like this, you know. Diverge, okay. I wouldn't want to say much about this, but please, it is just an additional information that might be helpful, because if you prolong, are you listening to me?
Yes.
If you make this line longer, this line, the line of the divergent, if you make it longer, they seem to be coming from a point. So I will just use dotted lines to show you that this is just a prolongation of the line, not necessarily that anything is coming from there. Can you see that? It's just a prolongation of the line. There's nothing really coming from there because it diverged. But if you make the line longer, it will appear to be coming from a point, which is actually the imaginary focus. Imaginary focus.
So what's special about this?
So, as a matter of fact, even a concave lens, we can actually trace the direction of the divergence. All we need to know is the imaginary focus. From the imaginary focus,
How do you know the angle then?
yeah, it depends on the focal length and some very important principles I'm going to mention to you. So we're not going to jump the gun, because let's take it line upon line, precept upon precept. I'm going to give you certain principles you will use to determine how it will go, the angle, the direction it will go. But there's an imaginary focus it can come from. From this imaginary focus, you will now know how it will diverge, whether it will diverge with a big angle or a small angle, and so on. But there's an imaginary focus. In fact, a concave lens has a negative, when you are carrying out calculation with lenses. For a concave lens, we use minus. The F, the principal focus, the focal length of a concave lens is indicated with a negative. The reason is because it's coming from an imaginary focus. Concave. Now for convex,
What's the focal point measure then?
I'm going to tell you, of course, the unit will be in the normal SI unit of length, meters. But of course, it can be rated in centimeters. Like, look at this one. What's it written in? 15 cm. So, of course, you can convert to meter. FL stands for what? Focal length. Is it not written on that? Focal length is 15 centimeters. You can convert to meter. That means the focal length in SI unit is 0.15 meters, right? And I will tell you how the implication of all this. All right. For a convex lens, I said. Why am I still writing convex on top of here? For a convex lens, the principal focus or the focal length is positive, or F is positive, because it actually has a real focus. You know, F is positive because it has a real focus. That's for convex lens. Remember, this one is concave. Or divergent lens, diverging lens. I think we've established that foundation. A quick summary: two types of lenses, convex lens or converging lens that bulges out, concave lens or diverging lens that curves in or caves in, right? It caves in on both sides. Now for a converging lens or convex lens, a ray of light incident on it, or rays of light incident on it, will come out meeting at a point, or converging at a point, and then of course they will still diverge after that point. So that's why it's called a converging lens. Now for a concave lens, rays of light coming towards it will spread or diverge, after they pass the lens. And that's why it is called concave or diverging lens. Now because a concave lens doesn't have a real focus, because it appears to be coming from somewhere. Remember, this is actually the direction of the light. It just strikes here and moves. It strikes here and moves. You may be wondering, why did this one go straight? I will tell you something about that. It just strikes here and that spreads.
Because it's parallel to that line.
I like that. That's part of the principles we're going to look at. Okay, so it just strikes here and spreads, strikes here and spreads. Yeah, I will explain all that to you. So, but it has an imaginary focus where the lines appear to be coming from. So that imaginary focus is the focal length when you measure it from the geometrical center of the lens. So the focal length is given as negative for concave lens. But for convex lens that actually focuses at a real point, the rays actually meet, the focal length is positive, or F is positive. Okay, let's take this a bit further. No, I need to introduce a line here. Let's go forward. Are you ready?
Yeah.
Let's look at certain terminologies we use for defining lenses. I think I can spread this one that I already have a note on it so that we can work faster. All right, that's fine. This is what we call principal axis. The principal axis is that line you were talking about, a perpendicular line to the plane of the lens. Oh, sorry, I'm mutilating this diagram. So this is the principal axis. It's a line that is perpendicular to the plane of the lens, the vertical plane of the lens. And the line passes through the geometrical center of the lens we call C. Since I can put up a better diagram here, let me just do all of this again so that I can use straight edges to draw it. Now if we have the plane of the lens as this line drawn in green, which is perpendicular to it, is the principal axis, PA. Principal axis, PA. Now remember, the one in black is the vertical plane of the lens, right? Now this position is the geometrical center. All right. One more time. This line is the principal axis, like the reference basic axis of the lens, and it is perpendicular to the vertical plane of the lens. This position, of course, is the geometrical center of the lens. All right. So the angle between the principal axis and the vertical plane of the lens is 90 degrees. That's why they are perpendicular. Of course, they all meet at the geometrical center, right? Beautiful. Now, where parallel rays focus is what we call principal focus. So now let me draw parallel rays coming in. Let me start with this. Hit this. Hit this. If the rays are parallel, once the rays are parallel, you know what I mean by parallel lines? They never meet. Once the rays are parallel, when they are coming out of the lens, also another one could have also passed through this, just run along the principal axis. Parallel rays, right, come out of the lens and meet at a position we call principal focus. It's not just focus, principal focus. I will tell you the difference between this principal focus and any kind of focus. So the principal focus is the point where parallel rays that pass through the lens meet. principal focus. So that's the position here. I label it. This position here is principal focus. You can call it PF. Now, it's different from any kind of focus. If you have a lens again, let's look at the lens. We are going to demonstrate this. You will see what I'm talking about. If you have a lens like this is the principal axis, and this is the vertical plane of the lens, and you have rays that are not parallel, maybe rays that are not parallel, they're still coming in, but they are not parallel, right? Or even not necessarily converging, but they are not parallel. Maybe I can use something like this. Not necessarily converging, but they are not parallel. You know. These rays are not parallel rays, as you can see. Check them out. Are they parallel?
No.
Now, they will still converge when they pass through the lens. You know, they will still converge somewhere. They will still converge somewhere where we call the focus. But this focus is not the principal focus. This is just where they are focusing. So it's just a focus, or focal point, if you like. Focal point. So principal focus is a special focus point that you have where when parallel rays that pass through the lens meet or converge at, right? Now, any other kind of ray or rays that pass through the lens, we still focus. I'm talking about convex lens. You know, it's a convex lens we are dealing with. All of this is about convex lens. So this is still focus. Now, remember this place is principal focus. You can call it PF. The distance from the geometrical center of the lens to the principal focus is what gives you the focal length of the lens.
You said the distance.
The distance from the geometrical center of the lens to the principal focus is the focal length of the lens. So I will label it. Interesting. Let's label it. This is it. This gives you the focal length, F, of the lens. This is not F, it is just a focus point. This is what I'm trying to say. Look at this. This distance from here to here is not equal to F. Did you understand this? What I do here, what it means?
F represents focal, yeah, that one is not.
It's not equal to F. Why is it not equal to F?
Why?
Pardon?
Why?
I should ask you. Why is this not equal to the principal focus? Why is it not equal to the focal length?
Because you know this, like slanted.
The rays that converged here were not parallel rays. Let me explain that again.
Oh.
The rays that converged here, even though they met here, the rays that converged here didn't come as parallel rays. So yes, this is the focus or the focal point. The focal point for those rays. And the distance from here to here, you can think of it as a focal length, the distance from the focal point to the geometrical center of the lens. But it is not, this distance is not the focal length of the ray.
So focal length is only when they're parallel.
Yes, the focal length, or small letter f, is the distance from the principal focus to the geometrical center. And you know principal focus is only formed by parallel rays. You know. All right, I think I have a summary of all this. Is there anything I haven't talked about here? Now, so remember from the geometrical center of the lens to principal focus is f, right? You may also want to measure f on the other side. Once you know the f, or it is given, you can also measure it on the other side. Sometimes you may even need to measure 2f. So if from here to here is f, from here to here will be the same distance on the left hand side. We also call it f. And then 2 of the distance from the other hand side, we can call it 2f. I don't know if you got what I mean. This is what I'm saying. If from here to here is f, like 3 centimeters, we measure another 3 centimeters. That will be altogether how many from C? I mean, if this is 3 centimeters, if we measure another 3 centimeters, how many centimeters from C altogether? 6, which is 2f. You know, if the first one was f, the distance to this point is 2f. You can also measure the other one to another point and call it 2f. There's a reason for all of this, and I will tell you. But before we do that, I would like us to go through a summary of what we've done so far, defining all the terms. Read what I wrote here. Okay. Is it opening at your end?
That's what I agree. Okay. Parallel rays usually from far distant objects pass through the lens and converge at the principal focus.
Yes, parallel rays. Parallel rays pass through the lens and converge at the principal focus. Only parallel rays will converge at the principal focus. In fact, the implication is, you see this lens we have here? If you have parallel rays, what is the focal length of this lens, by the way? I showed you. 15 centimeters, right? If parallel rays come in and pass through the lens, they will converge at 15 centimeters beyond it. Then that's where they will converge. That is if the rays are parallel. If they are not parallel, they will converge, but definitely not at 15 centimeters. Yes. Alright. Now, you get parallel rays from far distant objects, like the light of the sun. The sun is far enough. Once rays are coming from far distant objects, they come parallel. You know, there's a way you point a torchlight and it's spreading. They are not parallel rays. There's a way you can cause them to run parallel. You force them to run parallel, maybe using certain other materials, maybe a mirror placed side by side, you force the rays to run parallel. But for far distant objects like stars, the sun, once the rays are coming from there, they already come parallel. In fact, that is also that's what is going to help us to carry out this experiment we're going to carry out, to confirm the focal length of this lens. We're going to do that now. So let's establish some point before we do that. Okay, all right. Remember I said parallel rays usually from far distant object pass through the lens and converge at the principal focus, isn't it? But if the rays are not parallel, they still converge, but where they converge is not the principal focus, it's just like a focal point, like a focus. Like these rays, are they parallel?
No.
They still converge because they are passing through a converging lens. They will converge somewhere, but that's not the principal focus. Okay? All right. Remember the line, what I call this central line? Principal axis. You remember? Principal axis. And I call this one the vertical plane of the lens. And I call this the geometrical center. All right, so see the leveling. PA, which is from here to here, stand for what? C, geometrical center. PF, principal focus. All right. And of course, F, small focal length, which is from here to here. That's the focal length of the lens. Okay. So, we take it further. Let me now show you something that can answer some of the questions you asked earlier. Let's look at principal rays. Principal rays. Principal rays. There are three principal rays, like three basic rays that you can use to determine the position of the image formed by a lens. Three principal rays. There are three of them, but what we need is just two. The third one is already superfluous. It's not necessary. It's just a confirmation. Two will be enough. But let me talk about the three principal rays. Number one, a ray that is parallel to the principal axis will come out and pass through the principal focus. A ray that is parallel to the principal axis will come out of the lens and pass through the principal focus. Did you get that?
Sorry.
Let me read it out again. It's very important. Read it out.
The ray that is parallel to the principal axis will come out of the lens and pass through the principal focus.
Good. If a ray is parallel to the principal axis, it will come out of the lens and pass through the principal focus. Remember, this is the principal axis, PA. PA is the principal axis. If a ray is parallel to the principal axis, so I'm going to use this ray. Once it is parallel to the principal axis, it has to be parallel. This line is not coming out fine. I think I better use black. So a black pen is better. If a ray is parallel to the principal axis, once it is parallel, this line is parallel to this, isn't it? It will come out of the lens and pass through the principal focus.
Yeah.
To know the principal focus, all you need to do is just measure the focal length. So if from here to here is the focal length, then the principal focus is here. So let me write this so that we'll be able to indicate the ray. So such that the distance from here to here is f. So this ray, because it is parallel to the principal axis, we soon go through this so that you start the practical work. It's very, very important that you practice this thing. It's a highly practical class. It must be demonstrated for you to appreciate all this. If this ray, which is parallel to this principal axis, if it comes out of the lens, it must certainly pass through the principal focus. It must. You will ask it, how do we know the angle with which it comes out of?
Yeah, I understand that.
All right. So, for instance, I just don't want to disturb you with that. If we wanted to work with a concave lens, you can actually tell how it will move. If we already know the principal focus as here, and a ray is parallel to the principal axis. Remember this line? This line is the principal axis, right?
Mm-hmm.
And a ray is parallel to the principal axis, like this ray. It will diverge. It will spread. But when it is spreading, it will still appear to be coming from the imaginary focus. So all you need is to draw a line from the imaginary focus to where the ray hits the vertical plane and then make it longer. That will tell you the line that it will follow when it is spreading. The same thing for the other one. So that's the first rule or the first principle. A ray that is parallel to the principal axis will come out of the lens and pass through the principal focus. Always show arrows coming in, going out. The second rule is a ray that passes through the geometrical center will not bend. Any ray that passes through the geometrical center will not bend. Any ray that passes through the geometrical center will do what? Alright, so if we have a ray like this that passes through the geometrical center like this, it will not bend. It will just go straight. Assuming remember this is the ray 1 I talked about. This ray 1 is the one that is parallel to the principal axis, isn't it? Now this ray 2 is this second one. Oh, sorry, let me use a different color of marker for this second ray. It will be better, so that when I'm referring to it, I can just remind you of the color. I'll use a green color. Will the green be really separate, different? Okay, let me use yellow for this second ray. This ray that is parallel, that passes through where? No, I mean this yellow ray. Where is it passing through? Where it's passing through the geometrical center. So this is number 1. Can you define this ray number 1?
Parallel to the principal axis.
How did it come out? It converged and passed through where? Principal focus. Alright, correct. That's for number 1. Number 2,
No parallel to the principal.
how is not parallel, but how did it go? It's passing through the geometrical center. And what happened?
It didn't.
It just went straight, it didn't bend. Okay, so let me write it down. Number 2.
All points, all rays were meant to pass through the principal focus.
No, I didn't say that. It's only a parallel ray that will pass through the principal focus. We said that. Only parallel rays, or rays that are parallel to the principal axis, will pass through the principal focus. Only rays that are parallel to the principal axis will pass through the principal focus. All other rays we find different ways to pass through. But we have 3 important rays. The one that is parallel to the principal axis, that will pass through the principal focus. The one that is passing through the geometrical center will just go straight. Okay. There's a flip side of this second statement. There's a flip side to this second statement. What do you think should be the opposite of it? I said if a ray... No. It's actually a flip side of the first statement. The first statement is... Please, can I just write the second statement so that we have all of that captured?
Okay.
Let me note the second statement. Remember, the second statement is number 2. I'm going to write it in yellow. Number 2. A ray that passes through the geometrical center is not bent or does not bend. Maybe you put it like that. A ray that passes through the geometrical center does not bend. Let's reason it together. Look at this first statement. Can you read it out?
A ray that is parallel to the principal axis will come out.
Out of the lens and pass through the principal focus.
Yes, a ray that is parallel to the principal axis will come out of the lens and pass through the principal focus. Okay, can you think of the reverse of it?
A ray that is not parallel to the principal axis.
Or that's coming, the reverse of it is if this ray is moving this way. That's another principle of light. If a light can move from this particular position in this direction, it can actually follow the opposite direction and follow the same path. This is the statement. A ray parallel to the principal axis will pass through the principal focus. What will be the reverse?
A ray passing through the principal focus will be parallel to
Good. A ray that passes through the principal focus will come out of the lens parallel to the principal axis. So, I told you when you are doing this, when you measure F, measure the F again on the other side. Assuming this position is another principal focus on the other side. Because a ray could be coming from the right or from the left. Just like you have this lens, I was showing you. You can have the principal focus on this side and the other side, depending on which side the ray is coming in. If it's coming from the right, it focuses on the left. If it's coming from the left, it focuses on the right. So the ray can come from the left and focus on the right.
So there can be multiple principal focuses.
Yes, I'm definitely telling you that you can have principal focus on the left, on the right, depending on which direction the ray is coming from. So since we have the principal focus on this side, I can also indicate the principal focus on this other side, isn't it? And we said, I'm going to use a green marker, that if a ray passes through the principal focus, what will it do?
Passes through the principal.
What will it do?
Keep on.
No, say it properly. Remember, it's the opposite of number one. No, this ray.
If a ray passes through the principal focus,
Yes.
it will emerge from the lens parallel to the
Principal axis, correct. If a ray passes through the principal focus, it will emerge from the lens parallel to the principal axis. So let me complete the line. That's cool. All right. So Abdul, like I said, the flip or the reverse of number one is. Remember, number one is a ray that is parallel to the principal axis will come out of the lens passing through the principal focus. So it means a ray that passes through the principal focus will come out of the lens parallel to the principal axis. And did I tell you that you only need two principal rays to determine the position? Because let me tell you why I said you only need two. Look at the first two. This black one and the yellow one already met somewhere. When we drew the third one, it just confirmed it, so we didn't need the third one. Look at the black, yellow met here. So we just need two out of the three principal rays. If you draw the third one, it just confirms where the other ones already met. I can decide to use only 1 and 3, and they will meet here. If you like, if I erase these two, the second one, and only do 1 and 3, it will still meet at that point. So I need only two principal rays to determine where they will meet. Right? The third one is just to confirm what you have done. By the way, I write number 3. Can you say it out based on what I just said? Read out how number 3 will sound.
The principal focus can still.
No, I mean number 3. This number 3. Read out number 1 so that you use number 1 to know how I will write number 3.
A ray that is parallel to the principal axis will come out of the lens and pass to the principal focus.
Okay, a ray that is parallel to the principal axis will come out of the lens and pass through the principal focus. Okay, so how? That's number 1. How?
A ray that.
Yeah, go ahead.
A ray that is parallel to the principal axis.
Are you sure? That's number 3 you are reading now.
I'm confused.
You just follow
A ray
it.
that is not parallel to the.
I know it's not parallel, but where is it passing through? Remember, you are simply going to
A ray
say
that passes through the principal focus.
yes,
Will emerge from the lens and trace the principal.
and becomes parallel to the principal
Oh,
axis.
and parallel.
Yes. Let me write it. A ray that passes. A ray
Oh,
that.
sorry. I didn't know they had written that. I didn't look at number 2 yet.
Okay. A ray that passes to the geometrical center. Sorry, a ray that passes to the principal focus. A ray that passes through the principal focus will come out of the lens or emerge from the lens and pass through where and becomes parallel to the principal axis. All right, those are the 3 principal rays. Number 1, a ray that is parallel to the principal axis will come out of the lens and pass through the principal focus. That's this black one, parallel to the principal axis. Remember, this is the principal axis. Parallel to the principal axis will come out of the lens and pass through the principal focus. Number 2, a ray that passes through the geometrical center does not bend. This ray, yellow one, that passes through the geometrical center. Remember, this is the geometrical center. A ray that passes through the geometrical center will not bend. Number 3, which is the converse of number 1. If it is a converse of number 1, it means a ray that passes through the principal focus will come out of the lens and becomes parallel to the principal axis. A ray that passes through the principal focus will come out of the lens and becomes parallel to the principal axis. Okay, all of this is to achieve something. So I think we just try and practice some work to make sure you see the reason for all of this.